Welcome to the deep dive.
Okay.
So today we're doing something a little different. We're swapping out the dense academic papers
Right.
for what is really a masterclass in visual decoding.
That's all visual.
Exactly. Our sources aren't text. They are two highly complex geometric blueprints. And our mission is pretty simple: to look past the sheer volume of information and find the underlying architectural rules.
Yeah, it's really an exercise in pattern recognition. Because these diagrams, these screenshots, they're not just random art.
Wow.
They represent pure structural information that's been condensed into a visual language. And I mean, they're potentially overwhelming at first glance, but if you approach them systematically, that complexity it dissolves into a simple, beautiful order.
That's the goal. We aren't just summarizing what we see. We're trying to reverse engineer the thought process of whoever created this. We have to look past the sheer number of lines, what we might call the visual noise, to isolate the consistent signal. What are the minimal rules required to generate this massive system?
And that's our guiding principle for today. Geometry is the language here, but the conversation we're really having is about constraints. It's about how truly simple elements, a straight line, an arc, a circle, are combined systematically, repeatedly to generate these complete, visually complex universes.
Okay, let's unpack this. We should start with the first diagram, which, well, we've dubbed it the rounded trilobe because of its perimeter.
Good name for it.
When you first look at it, you see this soft, rounded, almost triangular outline. It's busy, but it's very clearly contained.
And the first thing to analyze is always the container, right? The structural definition of the boundary is absolutely key.
Okay.
The perimeter is so clearly delineated, not by straight lines, which would give you a sharp triangle,
Right.
but by three massive overlapping circular arcs.
Right.
And that's Geometry 101. Where circles overlap, they define precise points and boundaries. Those three arcs are the foundational law for everything that happens inside.
It's interesting that the boundary itself is curved. It sets up this great contrast with the interior, which is, well, it's almost entirely composed of straight lines.
Yeah.
The moment you enter that space, the visual density just hits you, with all these intersecting straight lines contained perfectly within that smooth, rounded perimeter.
And if you track those interior lines, you see immediately that they're not just floating in space. The entire interior structure is dictated by the constraints set by those initial arcs.
How so?
The straight lines are connecting points where the arcs intersect with each other or where they intersect with the overall boundary. They're not random at all.
It feels incredibly balanced. If you let your eye adjust, you can pick out a prominent, large, clear triangle right near the center. It's almost acting like the seed or the backbone of the entire system.
That's the perfect word for it. That foundational triangle is the key to understanding the system's symmetry.
Oh, okay.
The entire complexity hinges on what we call threefold rotational symmetry. If you imagine just spinning the diagram exactly 120 degrees.
A third of the way around.
Exactly. A third of the way around, it lands perfectly back on itself. That central triangle establishes the three dominant axes, and every subsequent line, every subdivision, adheres precisely to that 120-degree repetition.
Wait, if the complexity is generated so systematically, why isn't the density uniform? It looks like the center is way denser than the outer rings of the pattern. Doesn't a systematic pattern imply, uniform coverage?
That's a great question, and it speaks to the power of iteration. You're right, the lines begin by connecting the major points, forming that large central triangle.
Okay.
But then the next set of lines are generated by connecting the intersections of the first set of lines.
Ah, so it feeds on itself.
It feeds on itself. When you repeat that process connecting intersection points to create new, smaller intersection points, the density naturally compounds. It spirals inward toward the core, even though the rule set itself stays perfectly consistent.
So it's a self-referential density. And here's the detail that I think really locks the whole thing together. You can clearly see how the interior straight lines extend directly out to the bounding arcs. They don't just stop nearby, they connect right up to the perimeter.
Yes, that connection is proof of structural unity. The arcs are the physical limits of the universe defined in this drawing, and the straight lines, they act like tension members, locking that internal lattice to the exterior boundary.
So everything is tied together.
Everything. This is the core teaching moment of this first image. The system is entirely dependent on its edges. The interior structure is not independent of the boundary. It is a direct consequence of it.
Right. So we've established the trilobe structure, defined by three primary arcs, is a marvel of threefold symmetry and iterative constraint. Now let's pivot to the second diagram.
Okay.
Because this is where the geometric system it breaks loose. The increase in complexity and density is dramatic. It feels like the same engine, but scaled up exponentially.
It's a massive leap, and we see it immediately in how the boundary is defined. If image 1 was defined by 3 large arcs, this new structure's perimeter is formed not by arcs, but by a multitude of individual, contiguous, overlapping circles.
So not 3 big ones, but a lot of smaller ones.
A lot. If you start counting the boundary circles, you're looking at maybe 18 to 20 distinct circles arranged in a sort of flower-like or hexagonal packing pattern.
The perimeter itself already shows a much higher order of symmetry, but the core, the internal structure is what really overwhelms the eye.
Oh, absolutely.
You can contrast the open space we had in the first image with the center of this second one. It is just dominated by an incredibly dense, tight network of straight lines. It's a complex lattice that's almost visually opaque.
You move from recognizing a few clear triangles in the first image to seeing potentially hundreds of tiny intersecting facets here. The line density in the core is so high it nearly forms a solid mass.
Why, though? Is it just more lines?
It's the result of that same systematic construction rule being applied maybe 4 or 5 more times than it was in the first image. Every time you connect an intersection, you create a new one, and that leads to this exponential elaboration.
This level of detail, it kind of begs the question, what exactly does that mass of lines represent? Is this just a highly detailed flat drawing, or is it something more?
What's fascinating is that the drawing itself contains the answer, and this elevates the whole thing from a drawing puzzle to, like, a model analysis. If you look closely at the edges, you'll see faint cues. Tiny lines colored red, green, and blue.
The RGB lines.
The RGB lines, that is the smoking gun.
So those confirm this isn't just a 2D drawing.
Precisely. Those colors are the universal language of computer-aided design, 3D modeling environments. Red, green, and blue are the standard representation for the X, Y, and Z coordinate axes.
So this is a 3D object.
It strongly suggests that this hyper-complex lattice isn't just a flat pattern. It is a representation or a projection of a solid form constructed in a 3D environment.
Okay, so if we're looking at a 3D projection, that means the lines we see aren't just lines. They're the edges of geometric surfaces.
Exactly. Imagine taking a complex wireframe object, say a highly detailed soccer ball or a geodesic dome, and pressing it flat onto a page.
A projection, right.
The internal triangles and quadrilaterals we see are the facets, or the flat surfaces, of a much larger, incredibly complex volume. We're witnessing the visualization of a highly symmetrical polyhedron, a solid form, defined by all those circles on the edge.
That completely changes how we interpret the detail. In image 1, we recognize a few clear elements, but in image 2, the higher order symmetry, defined by all those circles, forces this exponential growth of line density, representing a solid object. It's the same geometric toolkit.
Lines and circles.
But the second image shows its full, overwhelming computational power.
Yeah, if we compare them directly. Image 1 focused on threefold symmetry, defined by 3 elements. Image 2 requires high-order symmetry, maybe 6-fold or more, defined by dozens of elements. The core takeaway is that transition from, let's say, contained elegance to just generated complexity through sheer iterative force.
So that brings us to the overarching question. We have 2 visually distinct patterns, the foundational trilobe and this dense, explosive 3D lattice. What is the single fundamental principle connecting them that you can carry forward?
Well, the synthesis is deceptively simple. Both of these structures are visual proof that overwhelming complexity can be generated using only 2 foundational geometric rules.
Just 2.
Just 2. Rule number 1. You define boundaries and key reference points exclusively using circles or arcs. Circles are the source of truth. They establish all the valid points in the system.
And what about all the straight lines, the stuff that makes up the bulk of the visual information?
That's rule number 2. You use precise straight lines to connect and subdivide space based only on those reference points.
So the lines can't just go anywhere.
No. The lines don't exist independently. They are slaves to the boundaries and intersections established by the circles. They are the mechanism of complexity, sure, but the circles are the intelligence behind it.
This is a really profound takeaway for you, the learner. These diagrams are visual proof of systemic organization. They reveal that structure, no matter how elaborate it looks, is being methodically, layer by layer, from simple, repeatable operations. You don't start with complexity, you generate it through absolute consistency.
And practically, viewing diagrams like these forces us to hone a crucial cognitive skill, pattern recognition. You have to learn to differentiate between the noise.
The sheer number of lines.
The sheer number of lines crisscrossing the page, and the signal, the underlying symmetry, the consistent connection of points, and the perfect adherence to those circular boundaries. When you can isolate those rules, the perceived complexity instantly dissolves into manageable order.
It fundamentally changes your perspective, not just on geometry, but on anything visually dense, whether it's a detailed architectural plan, or a piece of music notation, or even a complex data visualization chart.
That's a great point.
You stop seeing a spider web of randomness, and you start seeing a perfectly executed blueprint based on strict, simple constraints.
It forces you to practice critical thinking. For example, if you tried to find one straight line in image 2 that connected two random points, you couldn't. You would fail. Every single line is there for a reason, defined by the geometry. We are looking at a system that is fully integrated and logically coherent.
This has been a deeply satisfying visual analysis. I mean, moving from that foundational threefold trilobe construction right up to the massive complexity of the circle-defined projected 3D lattice.
And here's the final thought for you to reflect on. If such visually complete and intricate universes of lines and intersections can be produced by nothing more than the iterative application of simple geometric rules.
Lines and circles.
Lines and circles, what does that suggest about the hidden, invisible geometric frameworks that govern complex systems in the natural world? How often do we look at something complex, be it the crystallization pattern in a mineral, the branching structure of a nerve cell, or a system in physics, and mistake the visible complexity for true randomness when in reality it may be adhering to a perfect, invisible set of foundational rules? That raises an important question for you to explore.